This is going to be assignment 4, case 1, inviscid flow over a cylinder. Just like the previous videos, I'm going to be going over the general idea of how I got to my final solution and the results, because it takes forever to do this. So first and foremost, we'll work with geometry. Always make sure we're in our XY plane. To make this sketch here, all you have to do is go to the sketching tool, go to the rectangle, and you can just draw a rectangle from your origin of any size initially. You can go to dimensions, do general, and then drag off from each side, which will give you the ability to manipulate the dimensions here. In this case, I have used a 90-meter long by 35-meter tall rectangle, and I've put a small circle in the middle of 1 meter diameter. And to put the circle in, all you have to do is just draw circle, and then you can literally just draw your circle wherever you need to. Once that is complete, you can then go to Surfaces from Sketches, click that, highlight everything here, and then click Generate, which will then give you this gray surface you see here. Moving on to the meshing portion. Where are we at here? Beautiful. First, I will show you the mesh. And in order to get to this mesh, you're going to right-click, click Insert, and Method. The automatic method will give you a general quadrilateral dominant method. You can then click on the actual mesh tab here and adjust your element size to 0.2 or a different element size depending on the size of your system. Following that, you can right-click and insert a refinement, and the refinement is just going to make this look even better. I did refinement level 1 because my computer cannot handle refinement level 2. It just takes too long. For the name selections, this is very important. Our inlet is to the left, our outlet is to the right, our symmetry is the top and the bottom, and our wall is just this little cylinder here. It is important we name the wall because that's where we will be able to calculate and tabulate our lift coefficient, drag coefficient, and other forces. Once that is complete, we will be done. We can then move on to the next portion, which is, let me share the screen really quickly. This is the fluent. So now we can do our models. I first went and made sure to choose Inviscid model. For the remaining remaining parts of this case, there needs to be a viscous laminar flow and a turbulent flow, which we can use K epsilon and then the laminar one. So the same geometry is going to be the same and everything like that. So for this case, though, we are doing Inviscid. Okay. We'll go to fluid. We're just using air. Let that open. 1.225 kilograms per meter cubed is the density. Because we're Inviscid, we don't have to worry about our viscosity, so we can leave that alone. Our reference values, we are going to be calculating that from our inlet, like so. Our area is the area of our circle, which is just pi over 4 times diameter squared. Our diameter is 1, so it's just pi over 4. And again, our velocity is 10 meters per second. Now, when we go to our boundary conditions, we want to make sure that our inlet is a velocity inlet. And again, this is where we're able to change how fast we want our flow to go. After that is done, we can go to initialization, click hybrid initialization, and run our calculation. Because I was able to have a good mesh in a large enough area, my solution converged quite quickly, and the results I will show you here. First and foremost, we have our velocity contour, just to give you an idea of what this looks like. Console graphics, just like this. So let me zoom in a little bit more. So at 10 meters per second incoming velocity, as you can see, we have our stagnation points at the front and the back. Next, I will show you the CP contour, which is actually what's the most important part of all this, because we're testing coefficient of pressure. So this is what our coefficient of pressure is going to look like going around the outside of our cylinder. In order to plot this, we can go to XY plot. You can change the name to CP plot. You can click pressure, and then you can do pressure coefficient and curve length, which when you specify curve length, you basically just mean you're starting at this point in the circle and you're going around the entire edge until you go back. So eventually you should get like a periodic looking function. So this has already been done. So I will go to my CP plot, click Save and Plot. And as we can see here, our CP will variate between +1 and approximately -2.5. We're just about there, but not entirely close. And typically you would want to see a complete sinusoidal wave here. However, because this isn't 100% theory, this is a simulation, we have a little bit of a difference here. And I can actually very quickly show you this area here. We can see that the theoretical curve going around the edge of a cylinder should be, again, periodic. But as you can see, when we change our Reynolds number and things like that, we can have these plateaus like that in our function. So given that, we can tell that our graph does make sense. So that will, actually, no, I forgot. We need to also do our forces really quickly. Forces, I will print out the X direction. Print that, we'll go to console. We'll get rid of that. So when we print out all of these forces here, notice that our direction vector is in the X direction, and the force that is in the X direction is the drag force. And we're going to focus on the coefficients here, right in this area over here. Our total coefficient in the X direction is going to be our drag coefficient, which is, again, 0.2424987. And we should expect that that drag coefficient to increase as we increase in our velocity. So when we go from laminar viscous to turbulent viscous, we should see a rapid, or not a rapid increase, but just a increase in our drag coefficient. Moving on, I will very quickly go to the Y component, which will be our lift forces. Click print, exit out of that. And then for our lift coefficient, we have a negative 0.11166891. And again, typically in an Inviscid flow, you're going to have some type of lift, but for this specific case, again, because there's errors in computers and setups and things like that, so we're going to have a little bit of variation, but it is going to be very close to 0. So that will conclude the first portion of this assignment. This is going to be case 1 for the Inviscid flow. Thank you for watching, and stay tuned for case 2 of assignment 4. Thank you.